So another application of rate loss is looking at what are called plug flow reactors. Now, a plug flow reactor, typically a tube with some length L, some radius R. And what we see is that unlike the continuous stir tank reactor where the concentration is the same throughout the reactor, it's actually going to change as a function of length along the reactor. So what's happening is that this flow rate into the reactor is so high that it's turbulent flow. And what we mean by turbulent flow is that if we looked at a very flat disk of fluid, there's no concentration as a function of radius away from the center of the tube or spinning around. So we end up getting a little plug. And this little plug, ergo plug flow reactor, is going to look like a continuous stir tank reactor. So we're going to take the same approach we did before. We're going to say that accumulation equals generation minus consumption plus N minus out, our master design equation. Now again, we're going to assume steady state operation, so 0, A is a reactant, so 0. Now the complication with this is that when we had a CSTR, we had the starting concentration coming in and we had the concentration coming out. We don't have that anymore. What we have now is the concentration coming in to this control plug and the concentration coming out. So we're going to represent the width of this plug is dl, and so the volume here of our plug is pi r squared dl. So our N term is our concentration times our flow rate. Our outlet's concentration is whatever it is at dl times the velocity. Our generation, our consumption term here is the rate of reaction R sub A times the volume, which is minus pi r squared dl. So written down here a little bit more cleanly, 0 equals flow rate, concentration of A before the plug, so we'll say L, minus the concentration outside the plug, after the plug, L plus dl, times minus pi r squared dl times the rate of reaction. So we're going to divide here by pi r squared dl. We get 0, volumetric flow rate pi r squared dl, A evaluated at L minus A L plus dl minus r sub A. Now what we're going to further do is take the limit as dl goes to 0. What this is going to turn into is derivative. So we get v over pi r squared dA dl minus r sub A. Rearranging, r sub A equals v over pi r squared dA dl. So this becomes our governing design equation for this type of reactor. Now, depending on your rate law, if it's 0 order, first order, second order, third order, non-linear, Michaelis-Menten, it's going to really mess with how you solve this equation. But what you will get is an expression for what the concentration looks like as a function of tube length. So if you know what you want the final concentration to be, you can figure out what L needs to be. Because our bounds of integration here are at little l equals 0, concentration A is our starting concentration, and when L equals big L, concentration of A is whatever the outlet concentration is, we can solve this first order differential equation. So this is your second application. You can use your reactor design equation to go through and figure out if you had a plug flow reactor, what you expect the outlet concentration to be as a given function of length, or how long you need to be in order to get a desired concentration.